So we've done titrations before, and we've used an indicator. That's a visual way of telling when you've reached the endpoint. We can also look at the pH changes of a solution that we're titrating, and we can figure out when the endpoint has happened based on where the pH is supposed to be. Okay, so we're going to look at both of those things. First of all, remember that titration is a technique. It's used to find the concentration of an unknown solution using the concentration of a known solution. Okay, we have the analyte. The analyte is the thing we don't know, and the titrant is the thing we know. And we have to know the solution's concentration. Okay, there are two things that we talk about: the equivalence point and the endpoint. The equivalence point is the point at which we have stoichiometrically reacted the acid and the base, and there's none left. We've reached a neutral situation, or we've reached products, full products. Often you cannot see the equivalence point unless you add an indicator. When you add an indicator, you'll see a color change usually, and that color change happens at what's called the end point. The end point is the point at which the indicator changes color. If you do it really well, you hope that the endpoint and equivalence point are the same point. Okay, but that means you got to choose the right indicator, and you got to be real careful with your technique. We can create a pH curve, okay, or a titration curve by measuring the pH of the analyte, the solution we don't know, as a function of the amount of titrant that we add. So you could create a little graph, okay, and you could measure the concentration and you can measure the pH of the unknown solution versus the concentration of base that you add. If you plot the concentration of titrant added on the x-axis and the pH on the y-axis, you get a nice little curve. Now you might want to do this in concentrations. If your concentrations are very small, you might want to work in what are called millimoles. This is just an adjustment, another unit that we occasionally use. A millimole is the thousandth of a mole, as you would expect. Okay. Because of that, if you do millimoles per milliliter, you'll have the same as moles per liter, and that's molarity. The reason I bring this up at all is because often we're not using a whole liter of something. We're using smaller amounts, milliliters. And if you use moles in milliliters, the numbers get very small. So sometimes it's useful to use millimoles. The ratio stays the same because it's a factor of 1,000. If we react a strong acid and a strong base, so 50 milliliters of 0.2 nitric acid, 0.2 molar nitric acid, and a 0.1 molar solution of sodium hydroxide. Okay. If we start with no sodium hydroxide, so just the 50 milliliters of HNO3, it's a strong acid, so HNO3 dissociates completely into H plus and NO3 minus. Concentration of H plus is the same as the concentration of the acid. Take the negative log then, and you get 0.699. Okay. 0.200 molar HNO3, pH is 0.699, very low. What if we add 10 milliliters of base to this? Well, strong bases and strong acids don't rely on equilibrium. This is just stoichiometry. So 10 milliliters of the base, I can set up what looks like an ice table, but it's not really equilibrium situation. It's just stoichiometry. Okay, 50. We're using 50 milliliters of the HNO3, so 50 times 0.2 molar that's 10 millimoles. And we're using for the hydroxide 10 milliliters of a 0.1 molar hydroxide solution. That's 1 millimole. All of the hydroxide is going to go away because there's 10 millimoles of the H plus, but only 1 millimole of hydroxide. So both of those are going to react, 1 millimole of each, limiting reactant. And you're going to have 9 millimoles of acid left over. The total volume of this solution is 60 milliliters. Right, 50 from the acid and 10 from the base. So 9 millimoles in 60 milliliters is a concentration of 0.15. That's the concentration of the H plus. Therefore, take the negative log, and it's 0.82. So we went from 0.699 to 0.82 with just 10 milliliters of base. We've jumped up a little bit. Our curve is starting to go upwards. Okay. Here's a couple of more. Pause the video and take a look at these. So I'm not going to spend valuable video time going through the specifics of each of these, but this is the same reaction. We're just adding more base. So in part C, we've added 20 milliliters of sodium hydroxide. In part D, we've added 50 milliliters of sodium hydroxide. And each time we're calculating the pH just like we did. Here's 100 milliliters of sodium hydroxide. Here's 150 milliliters of sodium hydroxide and how it affects the pH. Okay. If I plot this, pH on the y-axis, volume of base added on the x-axis, I get an S-shaped curve. the change in pH is very gradual until I reach the equivalence point, at which point the change is very sharp. The slope changes to almost vertical. Okay, and then once I reach a higher pH and I add more base, the pH isn't going to change very much. Okay, so this S-shaped curve is a pH curve, a titration curve. And the equivalence point is the point on that curve where the slope switches sign. It's called an inflection point on this graph. And it happens for strong acid and a strong base that the equivalence point happens right at pH of 7. Okay, that's where the inflection point is. That would be the volume of base that you add that would give you a pH of 7, which happens to be, in this case, 100 milliliters of base. Okay. Now, what if you have a weak acid and a strong base? So we're going to start with 50 milliliters of 0.10 molar acetic acid, and we're going to use the strong base, again, 0.1 molar sodium hydroxide. Okay. So if we start with no sodium hydroxide, just the 50 milliliters of the acetic acid, we have a classic ice table. Okay. And we can calculate our H plus concentration in the usual way. We can make the approximation. We can take the negative log of X. We get 2.87. So that's our initial concentration. Now I'm going to do the same thing, incrementally adding acid in small amounts and see what happens to the pH each time. So if I add 10 milliliters of sodium hydroxide, okay, now I'm going to work in millimoles. So for the hydroxide, it's 10 milliliters times 0.1 millimoles per milliliter, right, which is 1 millimole, and 5 millimoles of the acid. So 1 millimole of each will get reacted. I'll have 4 millimoles of acid left over, and I'll have 1 millimole of the conjugate base. Okay? Now that acid, that 4 millimoles of acid, and the 1 millimole of base, I'm going to go back to concentrations here because I'm interested in concentration of H+. So this top ice table is like stoichiometry. This bottom ice table is the equilibrium concentration calculations that we do. Okay? And I plug that into my value expression for Ka. I get a value of X that's 7.2 times 10 to the minus 5. pH is 4.14. Okay? And I can continue on. There's the stoichiometry for adding 50 milliliters of NaOH to 50 milliliters of the acid. Notice there's no acid left over. There is some acetate ion left over, which is going to produce some hydroxide then, because it's a base. So we're going to produce a little bit of hydroxide when that reacts, and then we're going to calculate our concentration of OH minus, which is what X is. Take the negative log of that and subtract from 14, you get a pH of 8.72. I can do the same thing with 75 milliliters of the base and 50 milliliters of the acid. Okay. Now, look at this one, though. We have some hydroxide left over, and we have some acetate produced. That's two bases, so which one is most important? Okay. Well, if the OH minus is 2.5 millimoles, and there's only 5 millimoles of the weak base. Remember, not all of that weak base is going to act as a base, but all of that hydroxide will. The hydroxide is more important. So I can just use the hydroxide ion concentration because it's going to completely affect the base to get my pH. Okay, so the acetate concentration, the 5 millimoles per 125 milliliters, isn't going to really affect the pH all that much because it's a weak base. So it's not going to all completely dissociate. So you'll notice that the shape of a weak acid strong base is a much different shape. It's a shallower shape. Okay, and our equivalence point is a little bit harder to see. And you'll also see that as Ka changes, the Ka of the acid, as it gets smaller and smaller, then the curve gets smaller and smaller, and that equivalence point is harder and harder to find. The curve gets shallower and shallower as Ka gets smaller. Okay. So this is just a summary, 15.2, of what happens as you add, this is for 100 milliliters of weak base and strong acid. And you can see this is all done exactly the same way as the other ones. You can see how the pH changes. For a weak base and a strong acid, the curve is in the opposite direction, and the pH is lowering, right? You start with a base which has a fairly high pH. As we add acid to it, it lowers the pH. And again, you see this sort of S-shaped curve, and we can find the equivalence point, the point of inflection of that curve. and that'll tell us the point at which the base and the acid have equally reacted stoichiometrically. We're going to do one of these in class, and we'll make a pH curve, and you'll kind of see how it works, and then we'll take a look at how you can use the data to figure out the actual concentrations at the equivalence point. You can do it graphically like this and visually and take a look and sort of use a ruler and extrapolate, but there's a way to actually look at the data and figure it out too. It involves a little bit of calculus, but it's not that difficult. And we'll take a look at how that works a little bit later on.